what we do is choose from the menu a refactoring. So under my gen refact rules, what we can see is we've got a refact pipe intro. Here's some blurb on the right here about what we're going to do. If we like what we see over here, and you could obviously present this differently as a pop-up or as some sort of change in the code, then the code will be automatically refactored to introduce the pipeline. So you see down here, there are a few questions being asked. Once you just said yes, what's happened is it automatically refactored the code and introduced the pipeline. Now we can go further. For example, what we might want to do is to farm the read image and the write image. You can do exactly the same thing. All we have to do is select that. We choose the refactoring that we want. In this case, it's going to be please introduce the farm for us, the farm introduction refactoring. Same sort of blurb about what we want to do. You may have quickly noticed that down here there's a question: how many workers did you want? Right back to that point. Yeah, down here, it asks us how many workers did we want. So there's a bit of user interaction, a bit of programming interaction, just setting up the system and giving us the opportunity to interact with it. At this point in time, we're doing this manually, but in principle that can be fully automatic. It can be driven by performance or other concerns. So the number of workers can be inserted automatically. It can be a magic parameter. So the thing to see from the demo is what I've got here is a system which allows me to easily and largely automatically rewrite my program source, to introduce parallels in the source, to introduce these parallel structures, to produce the scale structures, and then to execute that. You may think, well, this is pretty trivial. All you're doing is just putting a few Erlang atoms in, and I could do that myself. Well, yes, you could. We took this to the Erlang user conference a couple of years back. We ran a tutorial, and it was very instructive to see how many people got it wrong. So a room full of Erlang experts, people like yourselves, we told them about the scale, and we said, okay, here you are, here's the scale, go away and use it. All we want you to do is to introduce a farm like this, and it's surprising how many mistakes people made. I probably shouldn't say this, but I think it's partly because you don't have types. Where's the exit? Good. Here's just to show you that this works. So this is to show you, so this is the naive parallelization. It's just a pipeline, and it's not much faster than this function. If we add in the two farms, then it gets a bit faster. But this one, as you can see, has much better scalability. It goes up to something like a factor of 10 on 24 cores. Don't have time to go into the detail of this. The point here is to show you that you can do all of this fully automatically, but you do need to try alternative structures. So one of the problems with imperative parallel programming is you bake in a particular code structure. If you're lucky, it works. If you're unlucky, you've got one of these ones down here, and then you're stuck. You can't change it. Big virtue of functional programming is flexibility, ability to change stuff. Okay? I think that's one of the messages I want to get over too. We also have some really large-scale demonstrators in the project, things like wastewater processing applications, numerical simulations, and so on, working on those at the moment. I'll tell you more about those if you talk to me in the break. This is just to show you that refactoring doesn't add much overhead. The dashed line is the perfect manual refactoring, sorry, the perfect manual coding. The solid lines are the refactored versions introduced using our tool. So in most cases, we're pretty darn close. We're exactly the same as the what you would do if you did this by hand. We've done it automatically. Big look. This is an interesting one. Anecdotal comparison of development times. Take this with a pinch of salt. But roughly speaking, if the development time is a certain number of days for parallel code, if you do it by hand, it's a certain number of hours if you do it using our tool. Okay. And we think we can get that down. This is still you have to figure out various things, and the tool doesn't quite work, etc., etc. Okay. quite impressive that you can save a factor of 24. Well, if you work 24 hours a day as a journal. Final thing I want to tell you about are hybrid skeletons. How do you get to heterogeneous systems? What we've done is to build on Scale plus a library, CL library interface into OpenCL code. What I mean by hybrid skeleton is one which can move between different processor types, CPUs, GPUs, etc., using semi-automatic code generation and a special set of refactoring rules. We called it Lapido after the hybrid Neanderthal human skeleton that was found a few years back. So for example, what we might do is to start off with our code. This is a particle simulation. We use a par map refactoring, which introduces the map, basically as we've seen before. So this is essentially as normal, introducing a map skeleton. And then what the hybrid map does is creates two versions of the executable code, one for CPUs, one for GPUs, and wrap that up with a little dispatcher, a scheduler, that decides which code should run on which system. There's a paper that we're writing at the moment. This is the library we're using, CL library, to do that. This shows you that it works. So here we have pure CPU versions. The red one is using an ETS, the blue one is standard. The red one's slightly faster, about a factor of 9 on 24 CPU cores. If you use the GPU as well, you can see you get much better speed up to this point here, about 18 on 20 cores, which point it flatlines, basically because you've run out of work. If you have more work, you can keep going. This is, we've submitted this to TFP, so hopefully we'll get this published soon. This one is more... Back.
So when you do the hybrid, you're both having a CPU core and a GPU core.
We have a CPU core and we have a GPU. The GPU has 448 GPU cores.
So by adding a ton of cores, you're able to do it faster.
That's right.
Okay.
A ton of GPU cores. You buy one GPU. You buy a GPU, right? You cannot go to NVIDIA and say, I'd like a GPU. They'll sell you a package of 192 or 2,000 or whatever the number.
Those graphs are a bit apple and oranges when we're talking speed up.
One GPU, one CPU.
Yeah.
The GPU is parallel inside because the cores are much smaller, they're specialized.
Check.
Yeah. And GPUs are not cheap yet. They will. The adjustment that I showed at the start of the talk, that's costs $192. You have 192 GPU cores plus the CPU ones. Quite cool. So now, this is just showing what happens when the GPU really kicks in. So what we're doing is we're running this application, the speed up for the hybrid version of the N-body application, 0 CPU cores, 1 GPU core, 220 times speed up, 1 CPU core, whoops. So the issue here is the CPU is basically throttling back the GPU. The GPU by itself is perfectly efficient. As soon as you add in a CPU, the cost of dealing with the GPU completely overwhelms the computation cost, and we just throttle back to the usual CPU style speed up. This is not actually too bad, it's about a factor of 20. It just looks bad, it's got 220 RPM. And that is fairly common. So you need to get the right code running on the CPU, right code running on the GPU. And if you're lucky, as with this one, you get good balance. If you're unlucky, you'll just use one or the other guys. There's no point. And we need to figure out how to do that. Great. So to conclude, the Megacore revolution is here. Computer hardware changing very rapidly. In fact, the Megacore era is coming to us. It's already here in the form of exascale computing, big data, very, very hot research topics. Heterogeneity, energy, both important. These are big challenges that the functional programming community can help with. Most of the programming models that we have are just too low level. They deal with concurrency mechanisms rather than mass parallels. Functional programming, on the other hand, through the use of higher order functions, through closures, through exploiting purity where we have it, gives us the ability to deal with mass parallels. We can create millions of threads, easily control them, avoid deadlocks, race conditions, etc. But there's still a lot of challenges. You've been a good audience. You've covered quite a few of the challenges today. So here are some open challenges. How do we deal with scale? How do we deal with processor hierarchies, particularly where the data is not all the same, the memory is not all the same? How to get the data to map to this? What are the best parallel patterns? Because we have a lot of them, so how do we choose the best parallel patterns and the best implementations of those patterns? That involves performance information. How can we find instance patterns within code that we don't know is patterned? How do we find the best mapping of these patterns then down to heterogeneous processes so we don't, for example, accidentally use the CPU where using the GPU would have been much more efficient? These are big research questions that are open at the moment. You can see some talks later on in the Erlang workshop that are going to deal with some of these issues. So I'm very excited to see those. Well, but is this wishful thinking? This is two rampant lambda men in St Andrews, Hank Barendrecht and Phil Wadler, discussing the possibility of functional programming in parallelism. Well, no, because the world is going functional. C++ 11 has lambda. C++ 17 is going to add parallelism as well as concurrency features based on closures, based on functional closures. And we can already build higher order functions in C++. So yes, we can deal with that. Java is going to will have or does have lambda, so we can use that. We can build on that in principle. There are languages like Scala, Clojure, Erlang, etc., all gaining, and Haskell, all gaining traction in the commercial space. So no, I don't think this is wishful thinking. I think this is a case where functional programming really can impact science as a whole. And we, in fact, have integrated some of these ideas into a plugin for Eclipse running C++ 11. So you can already take functional ideas, pattern-based ideas, and use them in a slightly more limited way than in Erlang in C++. Okay, so further reading. Thank you to our sponsors. There is a lot of money in this. Please join us. It's also very interesting to industry at various scales, including non-partners that I can't yet mention, but I hope you should run projects with large manufacturers. We need you. Please join our community. If you have any problems, if you have any large-scale applications, please tell us. Thank you.
Well, we've had an interactive session, but if anyone wants to
so this is nice that you can speed up a program by refactoring it, and that's what you want to aim for. But you said in the beginning there's so many different devices, right, and they will just explode.
Yeah.
So you will get all kinds of strange things. As a software developer, you want to push out code which fits most of those devices very well. And you're not going to have the device refactor your source code, recompile it in the device, and then spit it out, right? So that's that one you should use then.
You should use this, right? So what this does is gives the flexibility to use a GPU when we have it, or a CPU if we don't have it. So you can and we will also get automatic scalability. So the system here will scale the number of GPU cores that we have available, not only statically, but possibly dynamically. So if we're using some of the GPU cores, or we're using some CPU cores for some purpose, in principle, what we can do is say, well, actually what we want to do is to restructure, redeploy the algorithm and use a different number of cores. Now, deciding exactly when to do that and how many is very complex. But we're working with experts in machine learning who tell us that this is actually exactly their research area. So they are very excited by the possibilities here. We've got some good results in doing automatic choice of CPUs versus GPUs, for example.
Right, so it's not just a compile time thing, later on runtime you can still adapt.
You need as with all functional programming, you get the right abstraction. Get the abstraction as high level as you can, patterns, higher order functions, closures. Then, the compiler deals with the horrible, dirty bits. This has always been our philosophy. Don't let the programmer deal with all the dirty bits, because they might get it right. You know, they can always do, well, they can really do as well as a compiler, as well as a runtime system, if they work hard enough. But you can't afford to spend thousands of years parallelizing a program just to get a fraction of some performance out of it. And this system gives you the structure, you can then do that automatically. And that's one of the secrets of functional programming, this automation overload.
Okay, let's thank